Celebrating, as has been said a few times, 20 years of ADS-CFT. That's kind of a novel way to end conferences with anniversaries. And I kind of like the idea. Maybe we should continue. There are all sorts of anniversaries in physics. And it's good, I think, in general, for us to realize that physics is an ongoing field with a long history, a glorious past, magnificent present, and an even more magnificent future. And the time scale is really not 5 years or even 20 years. It's really the order of 100 years. We're somewhere around the 100th anniversary of quantum mechanics, which is still, we believe, is the overall framework for physics. Quantum mechanics, this is sort of when Planck wrote down his formula, and 91 years is when quantum mechanics was finally formulated by Heisenberg and Schrödinger. Doesn't have a discrete date as ADS-CFT. General relativity, we just celebrated a 100-year anniversary. These are the two pillars of modern physics, and they're roughly 100 years old. Quantum field theory came along right after quantum mechanics was formulated. A year later, you could attribute its beginnings, and it still is, in many ways, the fundamental framework for our well-tested theories in physics. And string theory is just about ready to celebrate its 50th anniversary, and maybe at the Okinawa conference we could celebrate 50 years. It's only half, that's as much halfway to 100 years of string theory, which began, again, with a discrete. We can date a discrete event in 1968. The Standard Model is a little younger, but it's rapidly approaching 50 years. And ADS-CFT is only 20 years old. But you can see that the time scale is roughly comparable. And many of you will live to celebrate the 50th anniversary of ADS-CFT. Now, the reason we pick out these numbers with zeros at the end is because we have 10 fingers. If we only had 2 fingers, we could celebrate anniversaries every other year. What have we learned from ADS-CFT? Well, I think there are 2 main lessons. One enormously important lesson, and one enormously important overall arching application. But the first one, in my opinion, is the unification of quantum field theory and string theory. And the second is the application of ADS-CFT to trying to unify quantum mechanics and general relativity. So, as instructed by myself, I will give reiteration of what the previous speakers said, some of the lessons, overall lessons, broad lessons that we have learned. The most important one, as I said, I think, is the fact that we learned that string theory is not truly a break with the framework of quantum field theory in the way that many of us thought 50 years ago, but rather they're identical, or more precisely, continuously connected and part of the same overall framework of relativistic quantum mechanics, whose boundaries we're not yet sure of, and whose structure we're just beginning to formulate in a deep way. Now, that has led to the ability to connect insights from string theory to quantum field theory and vice versa. And as has been remarked before, most of the insights have proceeded in this direction from the classical large-scale understanding of string theory or gravity to difficult problems in quantum field theory, and has given us enormous insight into strongly coupled quantum field theories, gauge theories, conformal field theories, critical phenomena, et cetera, et cetera. There has been less progress in the other direction, but clearly we've begun to have a tool which enables one to use understanding of quantum field theory, a non-gravitational theory where the principles are, we think, well-defined, and control in principle is at least in principle, is unlimited, to understanding the conceptual difficulties in string theory or quantum gravity, particular black holes, quantum gravity, and indeed just the structure of space-time itself, or emergent space-time. I also asked for a wish list. I have my own wish list, starting from easier problems to more difficult problems. So some of my disappointments in the last 20 years, and I admit, Hiroshi, that I was wrong about how long ADS-CFT would remain the central preoccupation of string theorists. But you know, there's another side of that. There are two reasons why one field or one direction is replaced by another. One is the one that you quoted, Poincaré, that it's rich and has applications to many different areas, and ADS-C certainly has fulfilled that beyond any expectation. But the other is that something better comes along, some new idea, which might be necessary, probably is, to answer at least some of my wish list at the bottom. First thing I really would like to understand is what happens when you scatter strings in flat space, where we can calculate things perturbatively, at arbitrarily high energies. There's nothing I can, well, and that seems to have very interesting features perturbatively, but we know nothing about it non-perturbatively, even though in principle ADS-CFT gives us a definition of the high energy string scattering amplitude in terms of a large radius limit of ADS-CFT correlation function. So there is a formula you can write, as people have written down, that expresses the high energy scattering, string scattering non-perturbatively, but that formula, which we can't use because we can't calculate those correlation functions in the appropriate limit, at least as far as I know, offers no insight into what happens at arbitrarily high energies if you scatter two strings. That, to a large extent, has to do with our lack of knowledge of 1/n corrections to the field theory, and that's indeed one of the directions, as many of the speakers have already said, needs to be improved dramatically. Then, of course, QCD string, which Ed talked about, which was indeed the origin of string theory, and continues to be, we all believe there is a QCD string, but some very interesting talks at this conference on attempts to develop that idea, but I wish I'll still be around to see the QCD string someday. And here, clearly, we have to learn how to deal with non-supersymmetric dualities, which, again, are a difficult problem that not too much progress has been made on. We need a useful dual theory of string theory in flat space. You can always take the limit of large ADS radius, but that's not, again, as I said, particularly insightful. We certainly need a dual of string theory or in de Sitter space. And finally, we need to address this question that many of the preceding people have raised, and Juan had some interesting speculations. Is there a non-perturbative definition of the bulk of string theory of quantum gravity? It's always conceivable that there isn't, that you just have those concepts as an asymptotic expansion, and the only way of defining these theories is in terms of the boundary quantum field theory. That, I think, would be disappointing, and I think is clearly conceptually the most difficult problem that faces us. Okay, so this has been an amazing conference. I think we all agree, and in a beautiful place, fantastic, but much too much food. But most importantly, the talks have been outstanding. They were very well chosen and organized. But they give after listening to a week of such incredible talks, you have to feel that string theory or fundamental physics is in great shape. I'd like to thank the organizers, by the way, for putting my picture up. Those of you who know Hebrew can see that it clearly is my picture. And finally, let us all thank the people who made this possible, especially Ofer. And Kobe and Shimon. They really did a magnificent job, as well as all the other string theorists in Israel who've contributed enormously to the success of this conference. In addition, there are many other people that Ofer will thank in a moment, as he knows very well how much he benefited from their contributions. But I would like to thank all the speakers. I mean, and especially the review talk speakers. So clearly part of the intention of the organizer of this conference was to allow young people to have more of a presence. I think that worked out beautifully, and the people especially who worked very hard to deliver such excellent review talks need to be thanked. So, toda rabah. Thank you all. But now I'd like to end with a word about future conferences. There's some feeling that I'm in charge of these conferences, which is totally false. No one's in charge. There's no committee. There are no funds. somebody, I think it was Spenta, referred to me, I think, as a godfather. I want to make it clear I'm not the godfather, and anybody who says that, I'll make sure that their legs are broken. So the only role I've really played is, well, at Santa Barbara we ran 2 conferences, and sometimes I've tried to urge people to step up. I did that with the Princeton group. They had a fantastic conference, and to some extent I did that here with this conference. And I think it's worked out beautifully. I even think that even though they worked very hard, and they feel that it was worth it. We certainly do. The great thing about the strength conferences is this sort of self-organized excellence, and it occurs all around the world. Next year, as we know, the conference will be in Okinawa, following year in Brussels, and the following year in South Africa. Now, where do we go from there? I haven't heard much, but there was a suggestion from some people in Vienna that might be. They're thinking perhaps in 4 or 5 years to hold the Strings Conference. Vienna's a beautiful city. I think we would all appreciate a conference in Vienna. I do come back to the point I made at the beginning of this conference, however, that, there are some places in the world which are great centers of string theory. You can identify them yourselves, which really should step up. And there's another interesting point I'd like to make is that, this is not a Eurocentric conference. There have been 2 conferences in India, 2 in China, 2 or 3, 2 in Kyoto, and so but there are 2 continents that we haven't visited yet, South America and Australia. So I'm not sure what that means, but I would hope that string theory penetrates to those continents as well. And with that, let me end and say Letroot, or see you all in Okinawa.
We should have questions also, but David.
Right. So now we have 8 minutes, right, for questions. And why don't all the speakers come up here so that they can deal with the questions? Go ahead.
So after these very general remarks, I have a rather specific question to Igor, actually. So, Igor, in your talk, you mentioned the possibility of looking for I'm here. Here.
Yes. Yeah. I'm trying to find a spot where I can hear.
Okay. Okay, so after all these general remarks, I'm having a rather special question about your talk. So you mentioned the possibility of looking for a gravity dual of a asymptotically free gauge theory. And so given the structure of the ADS-CFT correspondence, as we know, I think this is a pretty daunting task. And I was thinking about it a little, and I certainly wouldn't have any clue where to start. So my question is to you, do you have any clue where to start thinking about this question?
Well, I think Arkady Tseitlin and I actually once even wrote a paper of this sort, trying to address adjusted supergravity, like finding some kind of effective supergravity equations where you would see the coupling running logarithmically in the right direction. And there were other attempts along those lines. But I think, some people would have said it's from the beginning highly questionable because Sugra equations are a two-derivative approximation. So I would say that one thing we know about perturbative gauge theory is the importance of the higher spin currents. So the hope would be to somehow connect it with the higher spin version of ADS-CFT. But obviously it's not going to be easy, but I think it would tremendously enrich the field to at least make some steps towards asymptotic freedom.
So one of the curious things that I find about ADS-CFT is that the bulk seems to very conveniently package the physics in almost what seems a miraculous way, and yet we think of it as being emergent, and somehow maybe the field theory being in some sense more fundamental. So what I wanted to ask is, do you guys think that this almost a meta question of or should there be a new principle of sort of the convenience or elegance or compactness of packaging that we could be guided by?
Well, isn't that holography? The bulk there are no observables in the bulk.
Yeah, but we didn't come up on it by following that principle. So should we be, it's sort of, is it a lesson that's emerging? That's something we might sort of use more as guiding to go further from here?
Well, I think the question is probably whether there is a bulk theory that goes beyond the supergravity approximation, right? Gravity gives us this summary classically, and maybe there is some bulk theory we will discover that it's a universal packaging of information and processing information about quantum systems in general. That would be very interesting to understand whether it's true or not. Now, if you just think of it as an emergent phenomenon, then it's in other areas of physics that happens, right? You have electrons and protons interacting in a complicated way, and then you have something simple, let's say a solid or superconductor, some simple material, right? So the emergent behavior might be very simple and might be packaging these complicated interactions. But I think we hope the bulk is more than that.
Okay.
So, as many people pointed out, one of the guiding lights in this area has been black holes. And of course, contingent for black holes being a guiding light is the fact that we sort of recognize geometry as we see it in some simple Einstein-Hilbert type sense. In string theory, or perhaps other models like SYK or higher spin theories don't naturally admit black holes of this elementary kind. What should be our guiding principle in the more general context? What sort of what is the sort of prototypical object that captures the essence of a black hole for more complicated geometric phenomena that we would like to see emerge from field theories?
Well, I don't know, but there are black holes in string theory, so we can depart at least a bit from gravity. The SYK model also behaves thermally with chaos and so on. So there are other things. There is something more general, and yeah, if we had a general bulk theory, we would describe all these things. So. I mean, another point is that there is this notion that horizons and so on depend on our ability to observe our limitations, that they depend on our limitations. The fact that we can only measure simple things, and if we were to be able to measure everything, we would be able to see behind the horizon. And so understanding the theory of these limitations and why they're important for the bulk observer and so on it's pretty crucial because in the bulk, horizons are very, I mean, you cannot really see behind the horizons according to the bulk theory. So how do you get such a sharp division if the division on the boundary theory seems a little more murky? I mean, it's intimately connected to the immersion, but a similar problem has occurred in thermodynamics, in understanding how thermodynamics appears and so on. So it seems conceptually similar, and probably we'll understand it better once we have the bulk theory.
Yeah, just a comment that, say, when it comes to the dual of QCD, I would be happy with just the dual of the zero temperature theory, where there is no black hole. I mean, one thing that ADS-CFT taught us is that finite temperature creates a black hole, but we can just try to think about zero temperature theory, look for some kind of string worldsheet description, string sigma model or something. So any kind of bulk description at zero temperature would be great to have for class of.
Eric?
Yeah, so ADS-CFT came about when people were studying indeed limits of deep brains, and there was a lot of development in that time studying more general models of deep brains, and there was matrix theory and so on. Now we've learned a lot from ADS-CFT and the wonderful applications, but sometimes I feel we need to go back to what we were studying then, and there may be some elements that we need to sort of make further progress. Juan, you mentioned that in the bulk we may be not using the local Lorentz invariance, for instance, well enough, because we seem to use one direction basically as being the RG scale, but we don't see locally sort of how all these things fit together. So well, maybe I should turn this into a question. What elements should we sort of not go back to even, and maybe put back into the whole discussion of what we were already discussing before that ADS-CFT came about? Because so there's something special about ADS-CFT in the limit that we took. And we may have forgotten a little bit about the full generality and the full techniques that we have in string theory and in deep brains. So just a question about that.
Well, I mentioned strings 97. That was very much the matrix theory conference. And then there were some deep brain black hole talks. So yeah, I think you're right that it would be good to revisit some of the exactly topics from that conference. Like I mentioned in my talk, putting the one back in and thinking about this irrelevant deformation of dimension 2D that figured in David Kutasov's talk. But there could be all sorts of other related, I mean, maybe.
Kobe?
So far, the correspondence is a correspondence of a gauge gravity and rather than a string gauge duality. And as Igor, I think, mentioned, I mean, for hadron physics, for QCD, we need lambda order 1 and finite n. And the question is whether there is a hope that we will get it by introducing 1 over n and 1 over lambda corrections, or differently, one has to think about inventing a new model that will correspond to this the way that nature behaves at this region of lambda equal to 1 and finite n.
So actually, QCD doesn't have any, the only small parameter in QCD is the momentum of external probes. Sorry?
Well, in hadron physics, if you look on radio trajectory of baryons and mesons, then you identify that it has a stringy behavior with tension which does not correspond to large lambda.
No, absolutely. I'm just saying the only small parameter, like 1 over n, is external probes. Maybe just reinforcing what Igor said, that maybe one should focus on what it is in a dual that gives asymptotic freedom.
Yeah, so indeed, I agree with you that many of interesting development has mostly in terms of gravity and string theory. And there has been, for example, in this conference, there have been only very few talks with finite alpha prime. And I think it's really it's worthwhile to spend more effort into understanding string worldsheet theory in ADS5, CrossS5, for example. There have been some interesting structure, and there have been people who have studied some integrability properties and things like that. But I think that there is a possibility of developing this further. I think, for example, Juan and I tried earlier in the case of NS background, and that has led to some interesting insight into non-compact conformal field theory. And in a simpler setup of topological string, for example, that there is some more detailed understanding of how gauge string duality works from the worldsheet point of view, and that can be used to actually better understand. And eventually, in many applications of string theory, ADS-CFT correspondence, I think that the area of application could become much richer if we have more control in string worldsheet. So certainly, I think that's an interesting area that clearly need to have more attention, I think.
Yeah, I guess we don't have the framework of what kind of two-dimensional field theories we expect for these QCD strings. So that's one stumbling block somehow. But I think another approach that we heard a bit in the conference is bootstrap. So somehow maybe we know enough to implement a numerical bootstrap that will tell us what the masses are and so on. I mean, this is something many people here are pursuing. It sounds very interesting.
Okay.
I can't resist asking. So we've talked a lot about entanglement in geometry, but perhaps should we not be asking what is entanglement teaching us about string theory? How does entanglement sort of play into the perturbative description of the worldsheet string and perhaps more beyond? Is that something that one should be hopeful will teach us more about how the duality works?
Yeah, that's a very good question. I guess one perhaps simple question, well, a small variant of this, or a perhaps simpler case, is to ask if there is a simple formula for black hole entropy in perturbative string theory. So in gravity, we know it's the area of the horizon. It's a rather simple formula. But if someone comes up with the sigma model that describes the Schwarzschild solution, so that's a somewhat concrete sigma model, what needs to be computed to compute the entropy of that? And is that simple or not?
Maybe on a speculative note, a variant of that question could be, what would you do in the topological closed string theory to compute the topological entanglement entropy of the open string in some Gopakumar-Vafa or type sense? What would be the computation from the closed string point of view that gives you that entropy?
Okay, I think we're going to stop now because the tour is taking off and Ofer needs to thank the people who've made this conference possible. So let's thank the speakers.
Okay, so David already thanked the members of the local organizing committee, and many of them did a lot of work to make this conference possible, but there are lots of other people as well that were essential to making this conference possible. I'd like to first thank the members of the International Advisory Committee that gave us a lot of advice about the running of this conference, and many of them are here, so let's thank them. Financially, this conference was made possible by several granting agencies, by money from all the universities and institutions in Israel, and by several private donors, including Dudi Gershon, who is here, so let's thank all of those. I'd like to thank the technical staff and the video people that solved almost all the technical problems in this conference. Thank you very much. And last but not least, the practical organization of this conference was handled by Ricky from Tel Aviv University and by all the people at Dizenhaus, in particular Anat, Tzipi, and Magali, and they're all in the back there, so thank you very much. Okay, so we're going to have a final lunch now. It's going to be in the usual place, not outside here with the gynecologists. And the tour for Jerusalem will depart in 45 minutes. So, well, the last thank you is thank you all for coming here and making this conference what it was. So, thank you.